The broadcast is now starting. All attendees are in listen-only mode.
Afternoon, we're going to start talking about equations through the grades, starting from the very elementary and taking it up to some algebraic structure. So with that, let's begin. So what is an equation? We talk about equations, and so it is a mathematical statement that tells you that two quantities are equal. And in solving these equations or dealing with these equations, we use a combination of different algebraic, different numerical operations, such as addition, subtraction, multiplication, and division. But sometimes we can also call these not equations, but a mathematical model. We're talking about modeling two quantities or the relationship between two quantities, so we can start talking about, because in the Common Core they talk about modeling. So we can take these equations and start to talk about them as mathematical models, the relationship between two quantities, and finding out how these two quantities are related. So why do we need to study equations? That comes up. Why do I need to know this? So in dealing with equations, it's developing our thinking skills. How do we think? How do we think abstractly? How do we think quantitatively? And then it's talking about the analytical skills. Not only are we thinking about it quantitatively, we're thinking analytically, how do we solve it? What is the structure that we need? So when we deal with equations or mathematical models, it's a thinking process. It's helping us to develop our analytical skills so that when we get to higher forms of math, or just even real world, the ability to solve problems. We use algebra every day. I tell my students we use it every day, and students don't realize that we do. We use it finding change, finding unit rates. This is all using algebra and using equations.
Students use equations from the first time they begin to record mathematics. Now, we're going to make a distinction here. With the Common Core, there's a lot of mathematics recording going on in pre-K and K, and we're not sure that's exactly the best place to start having kids record mathematics with paper and pencil, certainly. So we're going to start with grade 1. So for example, in grade 1, we want the students to understand that when we put 2 items together with 3 items, this gives us a total of 5 items. And we begin this idea with the following. How many apples in all? So you have 2 apples in one box, you have 3 apples in another box, and you have a line pointing to when we put them together, we have 5 apples in the box. And then the students write 2 plus 3 equals 5. Now the 2 plus 3 equals 5 means that I have the 2 apples from the first box, the 3 apples from the second box, and then I have 5 apples altogether. The difference is, though, in reality, that you're not going to have, see, on the screen right now, we have 10 apples. We have 2 apples in the first box, we have 3 apples in the second box, and we have 5 apples in the third box. In actuality, we should only be talking about 5 apples, because 2 plus 3 is 5. So you have to be a little careful in dealing with, not so much in dealing with physical models, because if you have 2 apples and 3 apples, you put them together and you get 5 apples, but in dealing with pictorial models, because this pictorial model, although we understand it, can be somewhat confusing to students who are looking basically at 10 apples. We have to take care also that students need to understand what the equal sign means when they're using it to record what happens when they put things together. So they must also see that the equal sign can show the results when sets are separated. Now by this we do not mean subtraction. Let's give you an example. The students see 5 apples can be made into a box of 5 apples, can be made into a box of 2 apples, and a box of 3 apples. And they write 5 equals 2 plus 3. In this way, the students see that the equal sign is showing the equality or balance when the sets are separated, or when the apples are separated. But keep in mind again that we're not taking away anything. We're just showing that if 2 plus 3 equals 5, I can also show that 5 equals 2 plus 3.
This is an important property that students can see, because I know that sometimes when they deal in algebra, x equals 3 or 3 equals x, they want to know, does the x have to be on the right side or the left side? It really doesn't matter. It's just a matter of preference, and students need to understand that. So showing that 2 plus 3 is equal to 5, or that 5 is equal to 2 plus 3, is just dealing with the mathematical structure that I can write the 5 as 2 plus 3.
And unfortunately, in some cases in books dealing with algebra, there is a tendency to do a couple of things. Number one, always use x, which we think kind of should be toned down a bit. And the second thing is to always show that the variable, when you're solving an equation, the variable always ends up, or the unknown always ends up on the left-hand side. So you always have x equals something or a equals something, as opposed to possibly having equations where 2 equals a or 5 equals x, to give the students this kind of flexibility so that when they see an equal sign, it's not a matter of I get, it's a matter of I have 2 equal things. Because if they only see the equal sign in the form blank plus blank equals something, then especially in the early grades, and this we've talked to teachers about this, they begin to interpret the equal sign as saying, and then the answer is. So going back to our original equation, the 2 plus 3 equals 5, what you have to be careful of is that the kids don't see it as the following. 2 plus 3 equals means 2, if I add 2 and 3, I get an answer of 5, which really is what happens in this case, and then that's problematic. In fact, one of my graduate students had this happen to him. The book gave the students 2 plus 3 equals with a blank, and the students wrote in 5. They were very, very bright kids. Okay. Then the students were faced with the following. Blank equals blank plus blank. And the student wrote 2 equals 3 plus 5. Because what the student was saying is, I have 3 dashes, an equal sign, and a plus, and this is the way I write it. And we have to be careful in the lower grades with symbolism, because the children in the lower grades are not flexible enough to understand what the symbolism really means. They can verbally give it to you, they can verbally tell you what is going on, but when it comes to actually applying it to with the symbolism, there is some problem that they may have with this whole idea. In this case, the student just did not understand. They just knew how to copy the numbers. So we also believe the following. While being algebraic is something students in the lower grades cannot structurally understand. And I hope that some of you really really look upon this as we agreeing with you, because this is something that certainly first and second grade teachers almost fight every year. Students have 2 plus box equals 7. What goes in the box? According to what teachers have told us, the most popular, and by the way, the best wrong answer, BWA. Very interesting, this BWA. I'll mention something about it in a minute. BWA is 9. Why is it 9? Because children see a 2, a 7, a plus, an equals, and a box. And they know that the box, if they haven't had any experience or if they haven't had different experiences with this, the box becomes where the answer goes. Now for young children, the answer in many cases is the sum or the difference. In this case, because we're using a plus sign, it's going to be the sum. And when you get to this, they are going to say 9, because they do not have the flexibility, again, with the symbolism to say, well, it's 2 plus something equals 7. We don't believe that. We think the kids will see 2 plus and equals and 7, and the answer will be 9. Did any of you not know what the best wrong answer was? If you haven't seen 9 yet and you teach first and second grade, hold on. You'll see it pretty soon. And when we get to problems such as 7 minus box equals 3, many students begin to think that math is hard. And the reason for their difficulty with this is that at the early grade levels, the students do not have the cognitive maturity to deal with such equations. And let me say something here. We're not talking about ability. Basically, in my graduate classes and in my undergraduate classes in math ed, I do not talk about ability. I talk about cognitive maturity. For example, many children in first grade cannot read a clock. By the time they get to 5th grade, they can read a clock. And yet reading the clock seems to be one of the things that many people think is a 2nd grade objective or a 3rd grade objective. And why? Why is it such an objective? Why not wait for the cognitive maturity to kick in so that they understand what's going on in the clock with a clock? Same thing happens with reading the calendar for some children. They just don't understand what's going on with the calendar because they don't have the cognitive maturity to deal with it.
And that's an important piece because as they mature, they obtain or develop the cognitive maturity. And sometimes we are just giving the students the math that they really do not understand with the maturity level. And that makes math more difficult. And that's why they turn around and say, math is hard, I cannot do math. It's a progression. And if we don't wait for that progression to happen to solidify, then we're creating more of a problem because they just cannot do it. They do not understand it.
And yes, as far as we're concerned, the Common Core standards really, especially in the lower grades, do not deal with this concept of cognitive maturity. It's just a matter of the continued backward design of the mathematics as opposed to the backward design of the mathematics meeting the cognitive maturity growth of the students as they're coming up through the grades. And one of the reasons is that the equation 7 minus box equals 3 doesn't lend itself to being addressed using models that show 7 minus box balances 3. It's a very difficult thing to show. And this idea of showing it using the models is the first step in our M4 model of learning. This type of forced algebra really doesn't teach anything to students that is useful then, nor does it set the stage for what will happen in the upper grades.
So if you're forcing this, they just see it as rote, they just see it as a process without fully understanding how the algebra is built on our structure, our algebraic structure, our numerical structure. So therefore, this becomes the problem with students saying, I don't understand what the box and the x have to, or the variable has to do. So if you make them understand why we're using this symbolism, that would be very helpful. They don't see the relationship between going from a box or a triangle to a variable. That is, again, the progression that they need to see.
And one other thing, it's kind of an instance in my career, I one time had a 2nd grade teacher come to me in October and say she was trying to do missing addend, which is, 3 plus box equals 7, and the children were crying. That was it. They were not doing their homework. They were crying. They were very upset. And I basically, it was one of my first supervisory jobs, and I said, well, stop doing it. Give them experiences with manipulatives, with real-life objects on things that are missing, and then come back in the spring, in March and April, and pick up with the idea of writing out what's happening formally. And I think that's what we have to do. With some of these things, instead of trying to teach them right away, what we need to do is we need to give the students good physical and real-life examples of what would happen. For example, what if I have 2 apples and I need 5 apples, how many more apples should I get? Those types of examples to set the stage for what we want them to do formally as a terminal objective. but you can't do both of those very close together in time. One has to be done, the idea of the kinesthetic or the hands-on has to be done in the fall, early on in the year, and then the formalism done in the springtime. This does call for a resequencing of the curriculum, but we really feel it has to be done.
Algebraic thinking is having students think about the quantity without having all the values. So you're looking at using manipulatives and asking them to be able to look at this and manipulate with a physical model. And in the simple elementary balance, we look at two ideas with equations that you can do with your students as we develop these ideas using certain instructional ideas.
The first one's important. We only deal with whole numbers. This will teach algebra without the interference of problems with computation that occur when we involve fractions and decimals. And this is very important because we're trying to teach children the structure of the algebra. What happens when certain things occur and I don't know one of the quantities or I don't know two of the quantities? What is the problem-solving process? And the one thing we have found is that that's easier to do if we're not interfering with that process by bringing in other things that interfere with their learning or that they have problems, like fractions with fractions and decimals. And so our idea is that although we know that integers are considered algebra, integers are not considered, should not be considered algebra, and really in a sense integers should be postponed until students have a good idea of what's happening with algebraic equations and algebraic structures with whole numbers, and then bring in the integers as another number set. And this is the best way to handle it as far as we're concerned.
In teaching algebra at the community college level in a developmental education course, I find that students can do things right away because of their backgrounds using whole numbers. But the minute I put a fraction in an equation, they automatically tell me it cannot be done, they cannot do it. So I think that as we're talking here, what we want them to do is get that solid footing with being able to see how the number sentences are using the structure of, if I have the physical model, if I have 2 apples and then I have this box and I have 7 on the other side, what do I have to do, or what do I have to add to the 2 to get the 7? That's very easy by having them pair it off and looking at, okay, if I take 2 from here and I take 2 from here, because treating it as a balance, they can see it. Then once they understand that, then bringing in the other numbers of fractions, decimals, and then bringing in the integers. If we start throwing everything at them at once, what tends to do is they put all of these rules together and they don't understand what goes with what, when I add, when I subtract, when I multiply, when I divide, how do I get rid of a decimal in the later grades. It becomes, I'm teaching a graduate course and we started talking about numbers and solving equations, and they did not understand the mathematical structure that goes along with being able to do and why I do certain things. These are graduate students not understanding the mathematical structure. Remember, algebra is built on our structure, our properties, our operations, and they need a solid footing in that before we move on.
What we are going to do is we're going to show the power of the learning model by beginning with an elementary balance and manipulatives to teach about equations. And this is not new. This has been going on for many, many years. The first set of algebra tiles or algebra manipulatives I got was about, well, I'll just say it was close to 1980. I won't tell you which side of 1980 it was on. Maria's laughing here, but it was close to 1980. And it was done by a group out in California that was very forward-thinking about the way algebra should be taught. And really, in a sense, I did not really see it in any textbooks until about the mid-90s. So it took 15 years for this idea about how to teach algebra to get into textbooks. So it's a matter of we cannot depend upon the textbooks. We have to look elsewhere for our resources. and we will approach each idea using the M4 learning model. Now, we've used this before, we've talked about this before, and if you want more information, we will give you the website later, but you can just jot this down. What you do is, for the M4 model, is go to gdkmath.com and click on the About link. And when you click on the About link, there will be a video there that explains the M4 model of learning.
What's important about using the manipulatives and taking it through stages is that the students become very proficient in understanding the structure. And I think that's the important part. Remember, our Common Core, or our now New Jersey learning standards, as they're now going to be called, talks about coherency, fluency, and rigor. And that coherency is making sure that they could move through the steps in a very logical manner. The coherency of putting topics together, the coherency of that we're not doing all of this stuff without the depth of knowledge. The fluency is that they can move through these problems, again, having the structure. So using manipulatives, and I hear teachers say, oh, I don't have time. You do have the time. It doesn't take a lot, and what you're giving the students is that ability to see. Remember, that proverb is that I hear and I forget, I see and I remember, I do and I understand. So therefore, if they're moving in that manipulative, they're seeing the structure, they're understanding the structure.
One other thing about this, about the use of manipulatives, it sets up a model in the child's mind's eye. That's number one. And they remember models. They remember seeing things. They remember touching things. Number two, it has to do with what they call in psychological literature episodic memory. When you give children something to use and something to work with, and they work with it on an ongoing basis, they remember what happened. And that's when it gets into their mind's eye. So this idea that I don't have time, I had a very interesting experience many years ago. We were using algebra tiles with a group of students, and one student was a very, very poor student. And it was the springtime, and one of the students put an equation on the board and said 2a plus 7. And she automatically, after that, said, this was another student now, 2a plus 7, she automatically put down 9a. And the student in the back of the room, who was not a very good student, raised her hand and said very, very definitively, 2a plus 7 is not 9a because you cannot add a's and 1s. You cannot add bars and 1s. You cannot, and she started to replicate in her mind and verbally what she had done, what she had not been able to do when she was working with the materials. That is, take some bars and some 1s and try to add them together. You can't. So this idea that not having time is because of coverage. It's not because of learning. Because if the children can get that learning in their minds, then they can apply it, and then you can teach them how to formally show it. So now, before we discuss solving equations, let's discuss where they come from. We're going to look at something we did in our second webinar with number puzzles. And from this, we're going to see how we can discuss solving equations. In our second webinar, we looked at 4 steps in which a number puzzle could help develop an equation. Here they are. So we have language, we have manipulatives, and we have symbolism, which is basically a pictorial model of the M4 learning model. So we pick a number 2 to 5. In showing that, we use a bar for this number, so the manipulatives has a bar, and the symbol for that number is n. The second instruction was to multiply by 2, which means that we're going to double the number of bars and, in a sense, double the number of n's. So now we're going to have multiply by 2 leads to 2 bars, and that can be represented symbolically as 2 n's. The next step was to add 3. What we have here is we now have 2 bars and 3, and represented symbolically, that becomes 2n plus 3. And finally, multiply everything by 2. So we have in step C, you can see that we have 2 bars and 3 ones. And when we multiply that by 2, we double everything. And remember what I just said, we double everything. And that means that we're going to get 4 bars and 6 ones. And we're going to show that as 4n plus 6. Now let's go back and talk about doubling everything. When I said double everything, I meant we're going to double the number of bars and double the number of ones. And so from 2n plus 3 on the right-hand side, we got 4n plus 6. And if you look at that correctly, what we did there was we actually introduced and used the distributive property of multiplication over addition. We multiplied 2n plus 3 times 2. So it's 2 times 2n gives us 4n, and 2 times 3 gives us 6. And so we have here, in using the manipulatives, we can also start to talk about something as important as the distributive property of multiplication over addition. So after step D, we have our total. We've taken our number, we've multiplied it by 2, we've added 3, and we've doubled it. In this case, we used n, and we got 4n plus 6. This is the total, T, for the number n after we do steps A to D. So we have a formula, or a function, or an equation that can be read as T equals 4n plus 6. And let's just stop here and talk about vocabulary. Children very early on in their school career start to deal with formulas. You have the perimeter formula, you have the area formula. I guess the two are the first that they see. Those can be called functions. Those can be called equations. And here is where vocabulary may get in the way of the learning, because sometimes in our zeal to make sure that our vocabulary is absolutely correct, we kind of get off the beaten track in terms of what we're trying to teach children, and it becomes a vocabulary game. So be very careful of using words like formula, function, and equation, and try to get the kids to use them properly, but initially do not make a big deal of them until they really understand what's going on with the mathematics. After introducing what an equation is using T equals 4n plus 6, we can look at a more complex equation, such as 2a plus 5 equals 3a plus 3, and find the value of a. Now, let's just stop here and talk about this word complex. If I have T equals 4n plus 6, and then I go to 2a plus 5 equals 3a plus 3, that second equation is complex compared to the first one. An equation that says 1/2 a plus 2/3 equals 4/2 of a plus 5/6 is not any more complex than 2a plus 5 equals 3a plus 3. It's more difficult. The computation involved is much more significant, but the algebraic structure that Maria talked about is exactly the same for this equation, 2a plus 5 equals 3a plus 3, than it was for that massive equation of fractions and all that stuff that I just said to you. So keep that in mind, that making the numbers more difficult to work with does not increase the complexity. It increases the difficulty. And so the question is that you have to ask yourself, is my mathematics program making the mathematics more complex and stretching the thinking of my students, or is it making more difficult, which sometimes doesn't stretch their thinking, but certainly gets them involved in this idea of math is hard. We know at this point, when you have the equation 2a plus 5 equals 3a plus 3, teachers begin giving students rules for solving equations without setting a stage. So you'll hear things like you can add on both sides, you can subtract on both sides, you can divide on both sides, you can multiply on both sides. You can do a lot of stuff as long as you do it on both sides. But really, in a sense, do the children know what's going on? What is setting the stage? We talked about giving them all this information without setting the stage. What is it that we have with setting the stage? One of the ways we can set the stage is to find out where the equation came from. And we can find out where the equation came from by, number one, showing how the equation is built by using a balance. Number two, showing how we can record the results of building an equation. In this, we're going to use the M4 model that we have been discussing. And the M4 model has 4 instructional steps. First, we begin with only modeling using manipulatives. In this way, what we do is we have the children getting a hands-on experience with what we want them to learn. That's number one. Also, two, we start to develop language, oral language. The second step is to use the modeling to connect to the language and begin to write the language. So in the first step, we have them use the oral language to discuss what they're doing. Secondly, in the second step, we continue to use the model, but now we begin to connect it to the written word as well as connecting it to the oral language that we did in step 1. In step 3, we use the modeling to connect to the symbolism, but now we are going to we use the modeling to connect it, except this time we're going to connect it to the symbolism of the mathematics. And finally, the fourth level of the M4 model is to demonstrate the problem or the solution with the symbolism while continuing to use the ideas and the language developed in steps 1, 2, and 3. And you have to remember that sometimes people in using the manipulatives will use one set of language, and in going at a problem with symbolism will use a different set of language. And the children will be confused. Best example we can give is with division. When you are using manipulatives to show division, it's a sharing process. You're sharing things out equally to different groups. If I have 45 apples in 3 bags, the division says how many apples can I put in each bag equally. When we teach the division algorithm, it's basically goes into, or as I say, goes into. And so as a result, there's no connection between the actuality of what's happening, sharing, and the language that is used with the symbolism goes into. And we have to be careful of this.
As you use this modeling, this is what's starting them to develop and understand the arithmetic structure of our number system, about adding a number plus its opposite would give me 0, a number adding 0 to any number will give me the number. So we're building the arithmetic structure so that we go to algebra, we just move that structure along to the generalization. And so you need to go through the stages so that they really understand the structure and not just a process. Because if you look at the Common Core or the PARCC test, the tests are now asking the students to tell you or to analyze their answer by what strategies, what are the strategies that you used, and why did you use those strategies. So if they do not understand the arithmetic structure, they're not going to understand how to talk about the strategies and to state why they use those strategies to come up with the solution. So you're taking them through the stages and building upon it. And that's what math is all about. It's a building. It's stating that, okay, I'm going to start with the simple and go to the more complex by building upon it once they understand the structure.
So we have here a video that shows how to build an equation using the idea of a balance scale. And we will begin with the simple idea that 2 balances our unknown, A. We're going to talk about a balance scale and how we can balance things in algebra. here I have a balance scale, and on the left-hand side, I am going to balance 2 ones. And on the right-hand side of the balance, I'm going to balance that with an A. And I'm going to assume that 2 ones balances 1A. Now, I can add anything I want to each side of the balance, as long as I add the same thing to each side of the balance. So what I'm going to do on the left-hand side is I'm going to add 2 A's. But that means that I have to add 2 A's to the right-hand side of the balance. Now I've added the same thing to both sides of the balance, 2 A's, and that gives me 2 A's and 2 ones balancing 3 A's. I'm now going to add some ones to both sides of the balance. On the right-hand side, I'm going to add 3 ones, which means that I have to add 3 ones to the left-hand side. So now my balance reads 2A and 5 ones balancing 3 A's and 3 ones. And that's because we started with the balance that said 2 ones balances 1A. If you notice in that video, what happened was that we started with 2 and A as a balance. And so, by the way, in the lower grades then, it would be a good idea to teach the balance in science. It's a great place to teach balance, the idea of the use of a balance. Trying to do those with an actual balance takes some skill in terms of getting the materials to balance correctly. But at least using the balance in science gives the students the idea of what a balance is, and then you can use it in mathematics in a representational way with the balance scale and the pieces. Also, if you'll notice, I started with A on the left-hand, 2 on the left-hand side of the balance, and A on the right-hand side of the balance. And we did because we don't want to get the children involved in this idea that something is on the left equals something on the right. Both sides are equal. And sometimes people have a problem with that. The other thing also, too, is if you'll notice, one case I added something to the left side and then to the right side. And in the next step, I added something to the right side and then to the left side. It doesn't matter. It doesn't matter what you add to each side first, as long as you add both things to each side. And that's an important idea in terms of staying away from this restriction of what you can do in mathematics and opening up a lot more. So now we're going to look at how we take what we just did with the tiles and start to apply words to it, and getting into the idea of written language. We're going to construct a balance again, and this time we are going to write it out using symbols and words. So we're going to start with the balance that we started with before, which said that 2 ones balances 1A, and we're going to write that out. So we're saying that 2 balances 1A. Now what we did before, we're going to do again. We can add anything we want to both sides of the balance as long as we add the same thing to both sides of the balance. So on the left-hand side, I'm going to add 2 A's, which means that on the right-hand side, in order to keep the balance, I must also add 2 A's. So let's record that we add 2A to both sides. And now the result of that is that on the left-hand side, we have 2A plus 2 balancing on the right-hand side 3A's. Now, as we did before, we are going to add 3 ones to the right-hand side, and 3 ones to the left-hand side. And we record that. Add 3 to both sides. And what we get when we do that is, on the left-hand side, we get 2 A's and 5 ones, balancing 3 A's and 3 ones. And let's record that. So on the left-hand side of the balance, we have 2 A's plus 5 ones, balancing 3 A's and 3 ones. So our final balance is 2A and plus 5, or 2A and 5 ones, balancing 3 A's and 3 ones. What we've written here, 2A plus 5, balancing 3A plus 3. And the reason we have this balance is because we started with the original balance of 2 ones balancing an A, which we wrote up here, 2 ones balancing an A. And if you notice what happened, the language used in the second video was basically the same language that we used in the first video. And what we wrote in the second video was pretty much what we said in both the first video and the second video. And this is our idea of getting children used to a language structure that they can use in mathematics. Now, don't get us wrong. We want the children to have the use of proper language in mathematics. However, it need not be done immediately with the learning of mathematics, because then what you're doing is you're teaching children 2 different things that they don't know. Number 1, you're teaching them the mathematics, and number 2, you're teaching them new vocabulary. That's not the best way to do it. So now what we're going to do is we're going to see what happens when we take that structure that we've set up, how to work with the tiles, and the oral and some written language, and how now we can produce it formally to show how we can construct our linear equations using tiles and symbols. In our last video, we started with a balance, and we're going to do the same thing this time, except what we're going to do is we're going to write it in algebraic symbols. So let's start with the balance again. We had 2 balancing A. Now in the last video, we wrote that as 2 balances A, where we used this balance symbol to show that the 2 is actually balancing the A. In this video, we're going to write it as an algebraic equation. So instead of the balance, we're going to use the equal sign. So we have 2 equals A, and that's where we start. Now, going back to our last video, the first thing we did after we had the balance, or now that we have the equation, was we added 2 A's to each side. And we do that again. So we add 2 A's to each side. Now we show that as adding 2A to the left side and adding 2A to the right side. When we do that, if we look at our chart, we have 2A plus 2 balancing or equaling 3A. So we have 2A plus 2 equal to 3A. The next thing we did in our last video was we added 3 to each side. So let's add 3 to the left side and 3 to the right side. And let's record that. So we added 3 to the left side and we added 3 to the right side. On the left side of our balance, we now have 2A and 5, or 2A plus 5. And on the right side, we have 3A plus 3. So now we go to our equation and we record that. we have 2a plus 5 is equal to 3a plus 3. So now, from our balance, 2 equals a, we wrote the equation 2 equals a. And from all of that, we now have the balance 2a plus 5 balancing 3a plus 3, or the equation 2a plus 5 equals 3a plus 3. So now we have the idea that we have the manipulatives, the kinesthetic, still showing up. I mean, we talk about the kinesthetic level. We use the kinesthetic level, if you will, through 3 of the videos. Because what we want to do is we want to see how it matches up with the language and how it matches up with the symbolism that we want children to learn. In the 4th video, we're going to see how we take all of that and put it together so that we can just, in a sense, solve an equation. But as you watch this video, listen carefully to the words that are used, because you're not going to hear many different words from the other 3 videos. It's going to be basically the same oral language structure that will allow the children to understand what is going on. What we're going to do now is we're going to start with the equation 2 equals a. And we're going to construct an equation from that. So the first thing we're going to do is we're going to add 2 a's to each side of the equation. Now remember, as with balances, when you're dealing with equations, you have to add the same thing to both sides to keep the equality. The result of that is I add 2 a's and 2, and I get 2a plus 2. On the right-hand side, I have 1a, I add 2 more a's, and that gives me 3a. And since we added the same thing to both sides, it remains equal. The next thing we are going to do is we are going to add 3 to both sides. So on the right-hand side, I'm going to add 3, and on the left-hand side, I'm going to add 3. And the result of that is, on the left-hand side, I have 2 a's and 2 1's. Adding 3 more 1's gives me 2 a's and 5 1's, or 2a plus 5, equaling, on the right-hand side, 3a plus 3. So, what we have done is, from the equation 2 equals a, by adding to both sides certain things, we've constructed the equation 2a plus 5 equals 3a plus 3. So you've seen how an equation is built. As we said in the video, we began with 2 equals a, and we arrived at 2a plus 5 equals 3a plus 3. We did not do anything very fancy. We did not multiply on both sides, and we realized that, because what we are doing is setting the stage for allowing students to see the structure. And the easiest way to see the structure is just to add things to both sides. As you go on in the teaching of this, you could also have children multiply things on both sides. Multiply both sides by 2. That would be fine. We would have that's doable because you're doing the same thing to both sides. In a sense, also, this could be dangerous. If you wanted to, you could have the students take half of each side. That would be a little tricky, but you could work it out if you yourself use the manipulatives before you did it with the children. That's very important. Your homework is to become, in a sense, an expert with the manipulatives before you move ahead and try it with the children. Now, using the M4 model, let's begin with our equation that we just developed, 2a plus 5 equals 3a plus 3, and see how we can find the value of a. In algebra, this is called solving the equation. Again, we're going to start with the kinesthetic level, with the tiles, and we're going to take the equation 2a plus 5 equals 3a plus 3 and solve it. Or we're going to use the balance to find the value of a. Let's start with the balance of 2 a's and 5 1's balancing 3 a's and 3 1's. And what we want to do is we want to find out what would balance 1a. And this is the way we could proceed. First of all, on each side of the balance, we have a's. We have 2 a's on the left side, we have 3 a's on the right side of the balance. So let's take away 2 a's on the left side, but in order to keep the balance, we must take away 2 a's on the right side. So now our balance becomes 5 is balancing a and 3 1's. Remember, our goal is to get a on one side of the balance by itself. Right now we have a and 3 1's balancing 5 1's. So let's take away these 3 1's. We now have a by itself. But in order to keep the balance, we must also take 3 1's off of the left side. And when we do that, we've accomplished what we wanted to do. Namely, we now have a by itself on one side of the balance, and we're seeing that a balances 2. So, when I have the balance 2a and 5 balancing 3a and 3, that means that a will then balance 2. We're now going to look at solving this equation. Again, what we're going to be doing is taking the kinesthetic and the tiles that we used as the balance and move on to incorporate words to show how to start to record what's happening with the balance. Here we have our balance again. We have 2a and 5 balancing 3a and 2. And this time what we're going to do is we're going to record our balance. So on the left side of the balance, we have 2a and 5 balancing 3a and 3. Now remember, our goal is to get a on one side of the balance alone, balancing numbers on the other side. The first thing we did was we took away 2 a's. So let's record that. Take away 2a from both sides. And remember, we have to take it from both sides in order to keep the balance. When we do that, we now have on the left-hand side 5, and that is balancing on the right-hand side a and 3. Now, we want to get a alone on the right-hand side. So what we can do is we can take away 3 from the right-hand side. But in order to keep the balance, we must also take 3 away from the left-hand side. And let's record that. So we take away 3 from both sides. When we do that, we now have on the left-hand side of the balance 2, and on the right-hand side of the balance A. So we record that as 2 balances A. And now we've accomplished what we wanted to do. We now have a value of A, namely that A balances 2. To review, what we did was we started with the balance 2A and 5 ones was balancing 3 A's and 3 ones. And when that occurs, then we know from our work that A will balance 2 ones, and that is what we've recorded here, that 2 balances A, or A balances 2.
You notice in the video that when Frank got to the end, he said A balances 2, or 2 balances A. So he was reading it from the left to the right or the right to the left. So that allows students to see that makes no difference what side the A is on. And that's an important piece, as we said before, that you want to make sure that if I say A equals 2 or 2 equals A, they understand that no matter how I write it, it is the same solutions, because students are under the impression that the variable has to be on the left. Not necessarily, it means the same. It really gives them a sense that it's talking about equality, and that's an important piece, that whether it's on the left or the right, my answer is the same.
Very interestingly also, whether I look to the left or the right first really doesn't matter, because it means the same thing, and this is called a symmetric property of equality, which really is very much like the idea of symmetry. And so we have this property, and I'm mentioning this now because this is the way we see vocabulary being brought in and technical terms being brought in, not as part of the process initially, but as you get through the process, then you can start naming what the students do. Now, the next video is going to show you exactly the same equation with the balance, except this time we're now going to do it in a record it in a symbolic way that you would expect students to record in an algebra class or in a 5th or 6th grade class in doing linear equations. We have our balance here again. 2 A's and 5 ones balancing 3 A's and 3 ones. Now in the last video, when we did that, we recorded it using balance symbols. In this video, we are going to record it using algebraic symbols. So the left-hand side is going to be 2A plus 5. The right-hand side is going to be 3A plus 3. And instead of using the balance symbol, we are going to use the equal sign. So the balance, 2A and 5, balancing 3A and 3, forms the equation 2A plus 5 equals 3A plus 3. Now, again, our goal is to get 1A on a side of the balance. Well, on this balance side, we have 2 A's. Here we have 3 A's. Let's take 2 A's away from the left-hand side and 2 A's away from the right-hand side. When we record that, we say that we subtract 2 A's from each side. And let's see what we have left. On the left-hand side, we're going to have 5 ones. On the right-hand side, we're going to have A and 3 ones. So when we record that, we have 5 equals 1A plus 3. Our goal is to get 1a all by itself. On the right-hand side of the balance, we have a plus 3. So let's take away these 3 a's. So our goal now is to get a alone on the balance side. We now have 5 on the left-hand side and a and 3 ones on the right-hand side. Our goal is to get a by itself on one side of the balance. On the right side of the balance, we have a and 3 ones. So let's take away 3 ones from the right-hand side of the balance. That means we must take away 3 ones from the left-hand side of the balance. And let's record that. So on the right-hand side, we're going to take away 3, and on the left-hand side, we're going to take away 3. And the result of that, on the left-hand side, we're going to have 2, and 5 minus 3 is 2. And on the right-hand side, we're just going to have a, because 3 minus 3 is 0. So when we start with the balance 2a and 5, balancing 3 a's and 3, we end up with 2 balancing 1a. That means that the equation 2a plus 5 equaling 3a plus 3 is solved when 2 equals a. I think you'll notice that we're not perfect in making the videos. And Maria and I were laughing as we saw hands and all. That's our signal that we have to start over. And so we did. But getting back to the original point, if you'll notice, and I'd like you to take advantage of this when we go to the next video, if you'll notice that in both cases, both building and solving the equation, there's kind of a statement here that we could call an if-then statement. In other words, in the first part, we said if a is equal to 2, then 2a plus 5 equals 3a plus 3. If a equals 2. If a is not equal to 2, then 2a plus 5 is not going to equal 3a plus 3. And likewise, going back the other way, if 2a plus 5 equals 3a plus 3, then a equals 2. But if 2a plus 5 does not equal 3a plus 3, then a is not going to equal 2. There's a logic built in here that the students should not be taught, but they start to develop, that it's just not a matter of having an equation and getting any answer. It's a matter of having an equation and getting a particular answer based on that equation. So now what we're going to do is we're going to go to the next video, which would show solving linear equations just using symbols. We're going to start with our equation, 2a plus 5 equaling 3a plus 3. And again, our goal is to get a on one side of the equal sign equaling a value. The first thing we can do is we subtract 2a from both sides. (2a) minus 2a gives us 0, and so what's left on the left-hand side is just 5. On the right-hand side, 3a minus 2a gives us 1a, and since we're not subtracting anything from the 3, we have 3. So now we've created the equation 5 equals a plus 3. But again, we want to get a alone on one side. So let's subtract 3 from both sides. So we subtract 3 on the left-hand side, and we subtract 3 on the right-hand side. And the result of that is 5 minus 3 equals 2. And on the right-hand side, we have A. 3 minus 3 is 0. So we now have 2 equals A. So, in starting with the equation, 2A plus 5 equals 3A plus 3, we end up with the equation 2 equals A. And therefore, we have solved the equation 2A plus 5 equals 3A plus 3 with the solution that 2 is equal to A.
You can also see in the video that when we said 2A minus 2A is equal to 0, that's going back to the structure that a number plus its opposite is 0. So therefore, we're going back to the structure by using the properties. So that's an important piece for students to see as you move through the videos, that the structure remains the same and you end up with the correct answer.
Notice this type of work of modeling allows students to begin with more complex equations, and that's our keynote here. That really is the idea. We want kids to start with ideas that they can understand and yet are complex, not just too simplistic. This is very different than what you might see in a textbook. Here's an example. Some books and teachers give the students the following. Teacher, find the value of n for the equation n plus 5. Student, n equals 2. Teacher, how did you get your answer? Student, in 2nd grade, Mrs. Piaget had us remember that 2 plus 5 is 7, so the answer is 2. Teacher, but I want you to use rules of algebra. So to solve, you begin by subtracting 5 from both sides. Students are stunned. Why can't we just give you the answer? Teacher, because that is not algebra. Students, why do we have to learn algebra? Why can't we just give you the answer? And on it goes. And so for those of you who have seen some of this, you understand that if the problems begin too simplistically, the students do not understand the reason for the algebra. And as a result, the question becomes, why am I studying this, and when am I ever going to use it?
And that's an important piece. When am I going to use it? So I think an important part of studying algebra is when they're learning to solve these equations, they eventually start to think of them as a mathematical model, so that when they start doing the word problems, to show them that this is the reason we're studying algebra, is this thinking process to solve for these problems in the real world and pulling out problems that with just distance. Just if it takes me 3 hours to travel to my friend's house and they are 150 miles away, how many miles did I travel? It's just the very simple things of giving them a problem to be able to look at it and reason through it. Not even maybe sometimes coming up with the model as quickly as possible, but just reasoning through this analytical process of coming up with it to solve for these quantities. And I think that's the important piece that we're sometimes missing. You know, the Common Core says real-world problems. Yes, but they have to make sense to the student, and they have to come in a timely fashion to go through this.
Case in point about real-world problems versus real-world problems that don't make any sense to kids. Several years ago on the New York State regions, there was a problem about a taxi cab ride. And the question was, how many miles, they gave them all the information, and they asked how many miles did the taxi cab ride go. And not a lot of children got it, not a lot of students got it right, and there was some wonderment as to why students in the city, New York City, would not understand how to figure out how far the taxi cab went. And my answer was, because nobody does. Although it's a real world life problem, driving in a taxi cab, using the taxi formula and all, really in a sense, nobody, as far as I know in New York, at least all the people I've spoken to, ever try to figure out how far they've gone in the cab. They just basically watch the meter, pay the money, get out of the cab. So as Maria said, we have to be careful about what we see as real life problems. The question is, whose real life is it? Getting back to our initial idea about simple problems, there's a simple reason for this problem. Text and other algebra materials begin with problems for which students see no reason to use skills of algebra. The problems are just too simplistic. For example, n plus 5 equals 7 is not a barn burner in solving equations. And students already know the answer. So the question is, why have the algebra if they already know the answer? Teachers may say, but they have to know how to do these easy problems before they can get to the more difficult ones. But now you have seen our response. With models, students can do complex problems in the beginning. The modeling gives the students an avenue to see, number one, how the equation is formed, and secondly, how the solution can be arrived at. And in this, there is no magic. It's just algebra. And we hope that this demonstration today has given you the idea of what we see as algebra in the elementary schools, being something that's driven by a kinesthetic start, a language development, matching this kinesthetic and language to the symbolic so the children understand the symbols that they are writing, and finally being able to do it symbolically. This is not something that's going to happen over 2 or 3 days very quickly. In terms of grade level, we know of projects that have been done as early as grades 5 with these types of materials, and I would assume that people have tried it in grades 4 and possibly even 3. So in a sense, these are manipulative types of things that kids can understand because basically with equations, it's just the balance.
And what you really want them to see is that it's not magic, it's not hard, it's just relying on what I know, and if I could visualize it and manipulate it, I can understand it. And that's the important piece of having the students, because as they move on to the more advanced math, if they don't have the arithmetic structure and the beginning algebraic structure, they're not going to be able to do the advanced math. It gets all hung up into learning these rules and these properties without understanding the why. And in our state assessments now, this is the questions that they're asking. What is the structure? And remember, one of the standard practices is mathematical modeling. So you're giving them the ability to model with manipulatives and being able to transfer that, to take this transfer of modeling with manipulatives to modeling these equations with the word problems. What do these word problems tell me? How can I develop a mathematical model from my verbal problems? And sometimes it's using the manipulatives. Start with a word problem and ask them to take a manipulative to demonstrate this. It's all in the demonstration and the ability to look at this as moving forward in solidifying the basis of what an equation is, a mathematical model, and going back again to the structure. We want them to understand the structure, because when we start adding in the fractions, the decimals, the negative integers, that becomes a problem, because everything is put together with not having an understanding. So what we tried to do here is to show you that using the manipulatives and going through the 4 stages of the kinesthetic, the language, the symbolism, we're asking you that this is the way of the process of being able to have them become good math students. And that's what we want, the good math students, so that they have the basis of understanding. So we used our videos, and as we said, you can go on and view them on gdkmath.com if you want to. And so we thank you for joining us this afternoon. We hope that in these webinars we've given you something to think about in looking at the structure of which you teach and the strategies that you use. Thank you.